Let's jump straight into this explainer. Look at a typical Cambridge mathematics exam paper, specifically the 0580 syllabus. What do you see? A totally random string of numbers, right? Most students freeze up here. You've got students like Alex, who overloads his brain trying to memorize 100 raw math facts, but completely misses the underlying pattern. And then you have students like Sam, who rushes through, completely missing the actual command word requirements of the question. Today, we're doing things differently. We are going on an archaeological dig. Layer by layer, we're going to uncover the hidden algebraic clues in these sequences to reveal the perfect answer. By the time we're finished, you'll have the ultimate codebreaker's manual to crack absolutely any sequence they throw your way. Here is our map for the dig. We're treating sequences exactly like puzzles. We'll start with the foundational sequence language, progress through arithmetic and complex quadratic layers, shift gears into exponential growth like compound interest, and finish up with the top-tier shortcuts that will save you massive amounts of time on exam day. Section 1. To start breaking the code, we first need to establish the basic language used to label our puzzles. Just like a map needs coordinates, a sequence needs a strict system so we know exactly which number we are talking about. Understanding the notation is your first big step. We use the letter U with a tiny subscript number to denote the position. So U1 is simply the first term in your sequence, U2 is the second, and so on. But the absolute holy grail of sequence cracking and the command phrase you need to look out for on your paper is finding the nth term, written as UN. While a simple term-to-term rule just tells you how to hop to the very next number, finding the nth term gives you the master key to unlock any position in the entire sequence instantly. Think about it. If you need the 100th number in the pattern, you don't have the time to calculate 99 steps. You just plug 100 into your nth term formula and you're done. Moving to section 2. Let's look at our first and most straightforward pattern type, the arithmetic sequence. This is where the numbers follow a simple, constant step. In an arithmetic sequence, you are taking a reliable, constant step every single time. We call this step the common difference, or D. It's literally just the constant amount you add or subtract to jump from one term to the very next. For instance, if a sequence goes 7, 12, 17, 22, the common difference is simply a positive 5. You are just adding 5 each time. It's that easy. But how do we actually turn that into our master key formula to secure full marks? Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's look at the formula. Notice how our common difference of 5 becomes the exact multiplier for n. Because we add 5 for every new position n, our formula instantly starts with 5n. But wait, if we just use 5n, the first position would be 5 times 1, which is 5. Looking at our table, our actual first term is 7. So how do we bridge the gap from 5 to 7? We just add 2. Therefore, our final perfectly adjusted formula is un equals 5n plus 2. You multiply the position by the difference, then add or subtract a constant to make that first number match. Code cracked. Full marks. Section 3. What happens to our strategy when that first layer of differences isn't constant? What if the exam question fights back? Well, this is where our archaeological dig really begins. Consider this tricky sequence: 0, 7, 18, 33, 52. If we dig down to our first layer of differences, we get 7, 11, 15, and 19. They're not the same. It is not an arithmetic sequence. And this is exactly where a student like Sam might panic and give up. But we're not going to panic. We just need to keep digging. Let's find the difference between those differences. From 7 to 11 is 4. From 11 to 15 is 4. Aha! If you have to dig down to a second layer to find a constant difference, you've just uncovered a quadratic sequence. To secure the perfect answer, we use a specific blueprint that relies on 3 magic equations. A quadratic nth term formula always looks like this: a n squared plus bn plus c. We have to find a, b, and c. First, take your constant second difference, which was 4, and set it equal to 2a. So 2a equals 4, which means a is 2. Next, we look at the very first number in our first difference row, which was 7, and use the equation 3a plus b. Since a is 2, 3 times 2 is 6, so 6 plus b equals 7, meaning b is 1. Finally, we look at the very first term of the sequence itself, which was 0. The equation is a plus b plus c equals the first term. So 2 plus 1 plus c equals 0, meaning c must be -3. Our master key is 2n squared plus n minus 3. See how systematic that is? And if the puzzle goes even deeper, what if you have to dig 3 layers down to finally hit a constant difference? Then you've found a cubic sequence, and the formula steps up to 8n cubed plus bn squared plus cn plus d. You'll use this exact table of equations to crack it from the bottom up. Your third difference will equal 6a, your first number in the second difference row will equal 12a plus 2b, and the first number in the first difference row will equal 7a plus 3b plus c. It looks incredibly intimidating at first glance, but once you know the combinations, you're literally just plugging in numbers and working your way back to the surface. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at Ace the Exams IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's tackle Section 4. We need to look at sequences that completely change the rules of the game. These don't add or subtract to grow, they escalate through multiplication. Notice the massive paradigm shift here. Up until now, whether it was arithmetic, quadratic, or cubic, we were always looking at differences, what was being added. But in an exponential sequence, we are relying on a common ratio. We are multiplying. And because we are multiplying by a ratio, the numbers jump significantly faster. This is the hallmark of exponential growth, and Cambridge examiners love testing you on it. The formula for this is beautifully elegant. It's un equals a times r to the power of n minus 1. Let's decode that together. The letter a is simply your starting number, your first term. The letter r is that common ratio you are multiplying by. So if you have a sequence like 3, 6, 12, 24, you can instantly see we are doubling the number every single time. Your first term a is 3, your ratio r is 2, so your master formula is 3 multiplied by 2 to the power of n minus 1. And why n minus 1? Because on the very first term, you haven't actually multiplied by the ratio yet. Moving into Section 5. You might be sitting there wondering, when will I ever, in my actual life, use an exponential sequence formula? Well, let's look at the ultimate real-world application and a huge favorite for word problems on the exam. Let's talk about money. Let's treat this like a data scan challenge. Look closely at this table. Compound interest is the perfect example of exponential sequence in action. Imagine you deposit $100 in a bank offering 10% compound interest. A 10% increase means you keep your original 100% plus 10% more, right? So your multiplier is 1.1. Every single year, your new balance is multiplied by 1.1. It goes from 100 to 110 to 121 to 133.10. The interest itself is earning interest. That is your common ratio at work, allowing your money to grow exponentially, layer by layer. Let's scale that up for a high-mark exam question. Say you deposit $1,500 into an account with a 6% compound interest rate, and you leave it there for 10 years. Our formula says we take our starting amount, $1,500, and multiply it by our ratio. A 6% increase means a ratio of 1.06, so 1,500 multiplied by 1.06 to the power of 10. You punch that into your calculator, and you get $2,686.27. Subtract your original $1,500, and simply applying the formula shows you'll earn a massive $1,186.27 in pure interest. No guesswork required, just pure strategy. But exponential sequences don't just go up. Let's flip the scenario entirely. What happens when an asset depreciates? Think about buying a brand new car. Say you buy it for $10,000, and as soon as you drive it off the lot, it starts losing value at a rate of 20% every single year. If you lose 20% of the value, that means you retain 80% of it, so our common ratio is 0.8. Every year, you multiply the car's current value by 0.8. Now, here is a mind-bending mathematical fact that examiners love to test your understanding on. Because our common ratio is less than 1, the car's value shrinks exponentially, getting smaller and smaller, but mathematically, it technically never hits absolute zero. You're always taking a fraction of a fraction of a fraction. The numbers just get infinitesimally small. Finally, Section 6. Let's unlock the insider secrets. This is my absolute favorite part of the Codebreakers Manual.
The shortcuts. This is how top-tier math students manage their time matrix on exams, saving precious minutes by recognizing variations of sequences instantly, almost like they have X-ray vision.
Sometimes an exam sequence looks like a complex quadratic that's going to take you 5 minutes of algebraic digging to solve, but it's actually just a classic baseline sequence in disguise. If you commit this specific cheat sheet to memory, your square numbers, your cube numbers, your powers of 2, and your triangle numbers, you will be able to spot complex patterns almost immediately. These are the absolute foundation stones of exam shortcuts. Watch how this builds into an incredible time-saving hack. Consider a sequence like 2, 5, 10, 17, 26. You could calculate second differences, set up your 2a, 3a plus b equations. It's a ton of work. But if you have your squares memorized, you'll immediately see that this sequence sits right next to 1, 4, 9. Instead of doing pages of quadratic algebra and risking a simple arithmetic mistake, you can simply recognize that the second sequence is just the square numbers with 1 added to each term. The formula is instantly, magically, n squared plus 1. Recognizing these combinations is an absolute game changer for your final grade. We've covered a tremendous amount of ground today. Now that you have the complete Codebreaker's manual, from identifying simple arithmetic layers to digging for quadratics, scaling up with exponential ratios, and spotting those hidden square number shortcuts, you have the exact tools needed to crack any sequence pattern placed in front of you. You are no longer guessing. You have the master key. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.